So now we will get ready for our next item on the agenda, which is our Q&A panel discussion. So we have all of the speakers today with us that we just heard from, who will be on this panel, and we will be moderated by our fearless leader, Jose Castro-Perez. Jose is the Vice President of Product Management here at SCIEX. He is managing the whole product portfolio, including the CE, the LCMS, and the software ecosystems at SCIEX. And Jose comes to SCIEX with a very colorful background and experience in pharma, CRO, as well as the biotech industry. And in addition to this, he held several senior roles at Waters, where he focused on marketing and business development for the products and services they have. And now he's here with us at SCIEX. That he joined us in 2019 as a senior director for Accurate Mass. So he was originally my first manager. So now he is our fearless leader in product management as the VP. Jose, welcome as our moderator for the Q&A panel discussion.
Thank you, Tatiana, for the kind introduction. It's a pleasure to be here today with all of you. Excited to see all the work that is being conducted with our customers, and also how we're taking our technology further to advance science. So without further ado, I'm going to open up the floor. But before I do that, I'm going to reintroduce our panelists. So we have on the panel Tom Lim from Washington University in St. Louis, Michael Whitten from Helmholtz Munich, Francisco Jose Diaz-Galeano from the Universidad de Almería, Kirsten Neal from J&J Innovative Medicines, and Tatiana Talamantes at SCIEX. Welcome, all of you. Okay, so see you all. So thank you for that. I can see there's a number of questions coming through the chat. I'm going to read them out, and then I'm going to hand it over to any one of you that feels that can answer the question. So let's start with the first question that is here on the chat. With the amount of structured information present in an EAP spectrum, do you think it has the potential to replace CAD workflows?
I think there's a space for both technologies, right? So what we have seen, I think, in all presentations with EAD is that these interesting guys are this tiny little ones at the moment. So I think CID still has its place when it comes to tandem workflows, quantification, MRM type of things. But once EAD catches up with further development, and once we get these little hires to the major players, I think it might have the chance to replace CID. Once it becomes more efficient and really fragmented, this is something I didn't tell, but once you look to the spectra, there's typically a lot of precursor left. So there's still a lot to fragment in there. Once this is done, I think there is a good chances that EAD will replace CID.
Okay. Thank you. Thank you for that. So I have another, again, around the same topic, and MetID. This is for Nari. Obviously, you know, CID has been around for a long time as well, right? And it's been utilized for, you know, putative structure characterization in MetID. But the question here is that where do you see EAD going for, you know, drug metabolism in the future, and not just the gaps that, you know, one can address, but where do you see the future? What's the real need in MetID, you know, moving forward, both in discovery and development? I know it's a pretty complicated question. A lot of things there, but
yes,
just want to get your insight on that.
Agreed. I'll try to break it down into two parts then. You know, like I mentioned in my talk, the MetID is divided into sort of two sort of workflows. One is your sort of high throughput workflow, where you do a fast to identify soft spots, and you're working with your chemists, the medicinal chemists who are designing the molecule. So it's guiding the sort of drug design. per se. And having richer fragmentation and being able to do that fast, that's where the beauty of the time of flight instrument comes in for us. We want to turn this, like I said, into a workhorse. We want it to be doing things quickly for us, doing a fast turnaround, the ability to get both EAD and CID at this moment. And the CID that we get looks like HCD. So it's sort of even high quality CID. It's not low quality CID. So the 7600 becomes like a one-stop shop, right? Because it's giving you this sort of CID information. It's also giving you EAD, which is rich fragments. Now, that is great. You're getting more information early. If you can automate that workflow with the software, which is what we're doing with you guys, that would be very powerful. So that's one. Now, when you move into the development side, you cannot miss a single molecule, right? The whole idea is if you have a major metabolite that's circulating, you want to characterize everything out of it. And that's where having the sort of extra boost or extra fragments that are even hidden. And I agree, right now it's a mindset, because when you first look at an EAD spectrum, you go like, huh, where are the peaks? No, they are there. And they are all high-res peaks. Once you start looking at it and understanding it, it's very, very powerful. And that's what we are finding. So for your phase 2 sort of metabolites, it is a very powerful tool, especially for the glucuronides and that. So it has two. It has very powerful. It has different approach, like applications for your discovery workflow. It's also got a deep, when you do deep dives, it's very powerful. So that's, hopefully that answers, some of what you're looking for.
Thank you very much. This is a question for Kirsten Niels, J&J Innovations Medicine. So, the question is around, where do you see ICIF, UV, MS going in the future? Because right now it's very much focusing on charge heterogeneity. Obviously, I think there's potential for additional workflows in that space. What is your overall perspective as to where do you believe that technology will be moving into new areas within the biopharma characterization space?
I think overall right now it's good as a first look, and it would be great if we can get to localize it. So if there be some way to get to that localization of those mutations, so when we can say, okay, it's a basic peak, it's at -17, it would be really nice if we could drill down using EAD in that space and say like, okay, it is in this region, almost getting a charge with the peptide map all in one suite. I think that's the next level we have to take it to.
Thank you. So I have another question here, and this is more around focusing on potential quantitative aspects of, combining CID and EAD together, in particular to small molecules, whether there's small molecules, drug metabolites, or endogenous metabolites. And this is a question for Michael. In your view, your perspective, do you see any advantage of the combination in quant, leveraging both CID and EAD fragmentation to obtain a higher level of selectivity and performance of your assay?
Yeah. So at the moment we're combining both at the moment. So for our standard workflows, CID is actually the way to go, because this is where most of the databases are built on. So we still rely heavily on external databases, which have been collected on many instruments out there. So we go with CID in most of the cases. But once we dig deeper into the biology, this is where the people are really getting interested. Oh, where is this hydroxyl group? Where is the double bond actually located? This is where we top off the things with EAD in future. So what I'm actually dreaming of is a system somehow they say, look, this is the identifications we can get with CID. And this is problematic. You see that top hit and runner up, they are so close to each other, but they are different in a methyl group or in the position of a hydroxy group or a double bond, that maybe a software can suggest us, okay, if you would run EAD now on this, you're getting the information you want to. And this is actually what we're aiming for in future by collecting both information, that we somehow get an information system that tells us actually, okay, if you're going to shoot it now with EAD, you will get the definite answer here. So I think there's room for both. But as I said, CID at the moment is the standard in metabolomics. I hope we can change that in future, and I think it will change because people want to get more structural information. This is exactly where EAD comes in. So we always see EAD actually on top for all the answers CID can't give us at the moment.
Thank you, Michael. Interesting insights on your end there. Following along the same lines, here's a question for Francisco. From your point of view, and based on the work that you've been doing at the Universidad de Almería, what do you think about leveraging the CID, EAD for potential generation of libraries, right? Spectral libraries that one can leverage to obtain a higher degree of identification, quantitation, and what would be the effort involved to develop such a library?
In this regard, I think it was Michael who mentioned it before, that at the time being, you still have a lot of precursor ion left on your EAD, so you're not going down to sometimes as many different fragments as you could get. But I think it's going to be very interesting in the future when the technology continues to develop, and because we are going to find different fragments. For example, I showed the triazoles. So the triazoles have this M to Z ion of 70. That's common to all of them. So with this new fragmentation route, we can potentially find new fragments to avoid this kind of coelutions in the swath methods, and potentially have better information regarding our sample to make it easier in identification. And we have also begun working at the University of Almería in building databases on EAD for pesticide residues. We have tried different parameters to try to obtain a global view, and we're working now on selecting the best configuration possible for it's a multi-residue method. We're running hundreds of compounds, so it's always a bit tricky, but trying to look into what could be the best possible configuration for such a pesticide residue database.
Thank you, Francisco. So let's change gears a little bit. Let's talk a little bit more about large molecule characterization. This question is for Tom. This question coming through here around what are the unique advantages of electron-activated dissociation in top-down characterization for post-translational modification? How might this technique impact future proteomics research?
Oh, okay.
There you go.
Hear?
Yeah, we can hear you
Okay.
now. Perfect.
Yeah,
Thank
this
you.
is something that we constantly think inside the lab, because we do have all kinds of the fragmentation paths tools, including the OmniTrap, the UVPD, PDCR, EHCI, ETD, and EAD apparently, and CID in the lab. So we do have all the fragmentation pathways, all the fragments tools. But the point is that every fragmentation is giving a unique signature ounce. So I think the most advantage that we have to highlight from EAD or ETD or UVPD is that how efficient the fragmentation, like for example, EAD can produce the signature ounce for PTM analysis, because for some PTM is kind of okay to do, like the ubiquitination, GG tags, and the phosphorylation. If you can see the signature ounce, that will boost up the confidence of the identification and the quantification a lot, especially nowadays. People were doing the DIA and the SWAS, to use the MS2 for quantification. So those signature ounce will actually contribute to the quantification using the DIA or SWAS method a lot. And another thing that I want to bring up in terms of this perspective is that a lot of the PTMs are actually easily getting off from the peptide or small molecule samples. So that's a major challenge for CID versus HCD fragmentations. It's our experience that the EAD will actually have a less chance to lose only the PTMs on the different molecules. So I do see that as a big advantage using the EAD for the PTM analysis. Yeah.
Thank you, Tom. I've got a bit of a juicy question here. I don't know who may want to take this one. Maybe this will create another panel discussion here between all of us. But do we think that, given all the developments around DIA, data independent acquisition, that it will get to a point where, for large molecules, that there will just be that one acquisition mode? No need for DDA or targeted approach. It will all just be one acquisition mode in the future for simplicity's sake. So I'm just going to open this one up. So maybe let's start with Nari. So in your presentation, your workflow includes DDA, right? And I just want to get your take there. Maybe just go.
I think this is like you said, this is so juicy because this is when we talk to Eva, right? I mean, for software, and we have cadence meetings. This is something that comes up, and I think at this moment we are doing both sort of. We want a hybrid version because we want to start with a targeted workflow. Like we have these 100 things we're interested in, right? But if it misses, we also want the instrument to be able to pick up the things intelligently. So we want something intelligent going on in the background. And I think that's what Michael just said, right? All of us are saying the same thing. We want something that is smart, that if we have our targeted list, but if we are wrong, we want the instrument to pick up our mistake and fix it for us. And I think with the three modes that you have for us, especially in the small molecule workflow right now, the isotope, the DDA, and the sort of mass defect, I think we feel very confident that we will be able to pick up if we go with some sort of a hybrid workflow. And that's what we're doing. We're trying to set up these. So I'll stop there and I'll let others also answer. But I think something hybrid at this time where the instrument is intelligent and has some sort of AI or whatever it is we want to call it in the background, where it doesn't miss things.
Great points, Nari. I couldn't agree with you more. Who else wants to comment here?
I just love the way that Nari said it, that we want an intelligent instrument, because I'm always saying DDA is stupid, right? Just give me the 10 highest things. And okay, there's a bit of logic behind this, but it picks a lot of stuff. In some cases, it picks the right stuff. In some cases, not, right? So for me, what I'm dreaming of actually is a point where we always decide, do we do target metabolomics, do we do untargeted metabolomics? But there should be a point where we actually say we just do metabolomics, and data independent actually enables us this, that we say, okay, let's do everything. We fragment everything. We have a digital snapshot of our sample here on the computer, and then we can go targeted or untargeted. The big problem, I guess for all of us, I see here is also a software question somewhere in the poll. Software is being capable of reconstructing the spectra accurately. I'm always fighting with the proteomics people and saying, you are cheating, right? Because you know how the things are fragmenting. This is an advantage we don't have in small molecules, right? So for targeted workflows, it works beautifully, but the de novo reconstruction of spectra is something very complicated for us. You can work with EIC correlations on, but it will give you sometimes chimeric spectra, sometimes not. So it lies in the software, intelligent and good software at the end. I think the instruments are already there and they are capable of doing the things. The software that drives the entire thing is the big elephant in the room, in my opinion.
I agree with you. I mean, that's one of the biggest lifts that we have, right? Is to be able to take very complex data to a point that is meaningful, right? It's challenging. It has different challenges, whether it's small molecules, large molecules. But yeah, I mean, that's certainly something that I still think there's a lot that can be done to continue to evolve and develop the excision model, the software behind it. So anybody else wants to comment here? Francisco?
Yeah, I wanted to say that I think we're kind of getting there in some part, at least in the data-independent acquisition for targeted approaches, because I had there's more work, of course, that I didn't show, but we have been testing this xenoswalth DIA approach. We have been comparing it directly against triple quadruple for pesticide residues, and we are getting comparable results. I mean, we're talking about different devices from different vendors, and we are getting the same results applying the MRM mode in a triple quadruple and the swath DIA with the even to very low concentration levels in environmental samples. And the thing is that when we are done with the samples in the triple quadruple, of course, that's it. You have your, like Nari said, 100 compounds of interest, and you're done. You have nothing else. But now that we have analyzed these environmental samples in the Xeno 7600, we can also go look for additional metabolites of our found pesticides. For example, say I find acetamiprid, I can look for its metabolites, which at very low concentrations, which is something that we were not typically capable before. So it's true that for non-targeted, for metabolite identification, that independent approaches, maybe there's still room for improvement in terms of when trying to assign a precursor ion and the fragment ions compared to just the pure product ion scan. But for targeted approaches, I think we're getting there, if not there already.
Yeah, and obviously the advantages of high res is you can pick multiple ions, 2, 3, 4, 10 fragment ions to do your quant as well. So, but again, it puts a lot of emphasis on the software piece and the intelligence behind doing this in an automated fashion for sure. Tom, Kristen, anything else that you want to add here before we move to the next question?
Not from me.
Okay, great. Well, thanks. Kristen, anything from you?
That's nothing for me either.
Okay, all right. So the next question is probably requires another summit, but it's a big topic. The question is, what does the panel think about leveraging artificial intelligence on instrument tuning, data acquisition, data processing? This is a large topic. And this is one area that I'm actually very intrigued about it. I think there's a lot that can be done in this space to not just simplify the workflows, but enable us to get to answers in a much faster way, much more informed way. But I can see from everybody here on this panel, all of you are working on different areas, right? All very important. Advancing science, human health, making the food that we eat, a lot safer as well. But what are your thoughts on AI in general, in your workflow? What do you think that AI will do to solve the problems that you have, the bottlenecks that you have, and how will that empower you, moving forward? I know it's a heavy topic. So again, we're going to go around the room and get your feedback on that. Who wants to start?
So, regarding metabolomics, non-targeted analysis, I really quite fancy doing that, even if it's manual. If I have an additional tool that can help me, that's great. For example, in the data-independent acquisition to better assign fragment ions, precursor ion, that's could be a great tool. But I would really like to see this for targeted approaches, because as much as I like metabolomics and data-independent acquisition, I don't necessarily like routine analysis of samples, looking for pesticide residues, manually checking for the ion ratios, checking if everything is correct in the quality control. So these kind of things that can be automated, which is just, as I was saying, look at the ion ratio, look at the intensity signal to noise ratio. I think there's room for improvement in every piece of software I've tried about the automatic identification and quantitation of compounds. And I think it could be great to free us, those of us who are also working in routing analysis, free us more of our time for other more interesting tasks.
What do you think about, for example, instrument health, being able to walk up to the instrument and, have a self-diagnosis of the instrument, or even just like Alexa, right? You talk to the instrument and you say, hey, today I've got the samples I want to run. What is the best method that we can run? For instance, right? What do you think about? Do you think that will be the lab of the future, that you just talk to Siri or Alexa and it will just set things up for you?
I had never really thought of that. I mean, coming up to the instrument, talk to it could be interesting. Depends on how much you can get out of it and how clever your instrument is. Because we were just discussing precisely in my Q&A how to control the instrument. We were discussing about the typical spreadsheet where you have your control compounds and you can see the area and you can just by a glance, okay, the instrument, I really need to clean this. I shouldn't have injected this honey sample. It's made the instrument very dirty. So if it's something that it can automate, it can take time away from you. Could be interesting. Everything that takes time off your backpack in terms of routing, I think that's better for every scientist.
And I think what you just mentioned is really good, because normally we also have the spreadsheets. You see really, there's the dip coming now. And then it's often too late already. They say probably the last samples you have measured, they could have been better. So AI could really help you say, okay, you know what? In 2 months from now, you should do a maintenance or something. That would be a clever thing to do. So really having early feedback of these things.
Great point, Michael. Nari, you were just about to say something.
Yeah, so I think this would be very powerful, because we often struggle with, not everybody has equal levels of expertise in mass spectrometry, right? And you often have operators with different skill sets, different levels of skill. So having something like this, like AI incorporated into data acquisition, I was thinking, you really shifted my thought process there, Jose, because I was thinking back end and data processing, and I have numbers for that, but you really okay, so if we put all this intelligence in the front end of the instrument, if it guides you, I think it would be a very powerful tool for the lab to use in general. And I think it kind of makes more people happy to use the instrument, increases consumer confidence. I think there's a whole lot of things that can come out of this. But I'd also like to add the back end. We are actually doing, AbbVie is heavily investing in sort of bioinformatics. And we often have a bioinformatics person paired with us. Nothing replaces the old-fashioned going in and manually processing the data, but we are getting up to 90% there with our AI and those type of efforts. So that's way better than the 70, 80% where we were. So we're still not there, but I just wanted to put that out there, and others can expand on that. And I would like to hear where others are sort of with this. But
great
front end
insight.
would be awesome.
Great insight, Nari. Great insight there. Anybody else from the panelists who have an opinion here on AI in general, in our daily routines or analytical or bioanalytical workflows? No, I'm going to ask Tatiana. What do you think, Tatiana?
I knew you were coming to me. I would love, I don't spend all the time like you guys do in front of the instrument. I want to make the instruments better for you guys, but I think it would be awesome if we could have a self-diagnosing mass spec out there. And it tells you, hey, in a month, I need you to do X, Y, Z. It tells you when your sensitivity is about to be done, except everything that you all said is everything that I have dreamt of. And if I were in the lab, I would want that as well. I think we have great opportunity to implement machine learning and AI in our tools, because at the end of the day, we want to be efficient. We don't want to spend all the time troubleshooting or doing that routine work where, it takes us away from getting the opportunity to do on the things that we actually care about, coming to the result, the answer, the decision making to do the next thing. So I think AI ML is an opportunity that we need to implement in software and hardware. So yeah, I'm excited to work with the R&D teams to make our products better for you guys. So.
Thank you, Susanna. I have another question here in the chat around what software tools are used today for EAD from metabolites, small molecules. I would imagine these are either xenobiotics or endogenous metabolites. So that's a question from Michael. And
so as I mentioned, we use Sirius, although it was not made for this at the moment. So as I said, we're working with Sebastian to make it possible for this. And at the moment, well, it's a good old McLafferty. I have the book somewhere here. We have to go back, really good old chemistry, rearrangements, and all the thing. I think there is nothing at the moment that could really help you for complete automatic analysis. So we see it with EAD. First thing we had to learn is with CID, you never think about radicals, right? And you see, that is just mass off, right? Calibration was wrong, something, and then you realize, oh no, that's radical fragment, right? So it should be that mass. So everything is correct. So at the moment, it's a lot of manual effort in there, which of course then we could leverage for some AI-based tool, but we first need to really understand what's going on in there. So actually, it's back to good old chemistry, gas phase chemistry, I have to say.
Thank you, Michael. Nari, what tool do you use for your EAD?
Yeah, at this moment, I think like Michael said, our main tool is our own hands and trying to do the sort of organic chemistry workflows. We have our own home-built software, which is all the biotransformations that can happen to a molecule, phase 1 and phase 2, which we then use to prepare lists. But we also use Mass Metasite for our discovery workflows, and we're beginning to use all of the SCIEX tools that are at our disposal. That's probably, and then we want to see if we can combine our home build. That's why we're talking to Eva, and we have all of those bi-weekly meetings. Can we leverage the SCIEX software and combine it with what we have?
Thank you. So we have time for maybe 2 more questions here. The next question is around SCIEX has had a large impact in coupling with MS for a number of years now across multiple research areas. ICIF being the most recent example. How does everyone see the role of SCIEX versus LC? So maybe we start with Kirsten here.
Sure. This is a bit of a.
So do we see more of the, let me just rephrase here, right? I think the question was basically around, do we see an uptick on SCIEX coupled with mass spectrometry in the future versus a true untested LC as SCIEX progresses, interfaces progress, and so forth, and become more of a routine analysis, more like, for example, the ICIF, UBMS, right? That's become specific to one workflow and it does really well. Do we see that in the future for SCIEX where we start to see more of not just a niche area, but more used in a similar way as LCs today?
Yeah. So I think the CE space is particularly large molecule, right? So when you're talking about biotherapeutics and especially on the horizon, the ADCs coming out, the ADCs and any large molecule, you're always going to have a CIF spec, right? It's never going away. Charge is always a attribute. So I think the power of the MS on the back end of the CIF is where everybody in industry will appreciate the bang for the buck and lowering the investigations and having a more thorough filing for the FDA for any regulatory authority, right? Usually you go in with saying, your spec is an FYO, and so you obtain many batches, right? And then you can kind of set a spec on your acidics and your basics. This kind of drills down into saying, okay, is your process under control? It's under control. You know, is there deamidation? Is there clipping? Is there a genetic variant? Is there something that is of a concern? It also helps with drug product development in the large molecule space on them getting a formulation that, you know, if there's something on the charge side that it could be an issue on stability, they can design a formulation to make that more stable. So I think it will always stay in the large molecule space, and the you know, I don't think it'll take away LC because the CIF is a standard practice, but I think it will support many of these newer modalities coming on board. So ADCs are very hot right now, and with the ADCs and the DAR conjugation, depending what conjugation you're doing, it can help look at the unfolding and the stability of the DAR conjugation.
Thank you,
I
Kirsten.
hope that answers the question.
Yeah, absolutely. Great insights there. Tom, do you have anything to add here from your end?
I'm not an expert on this, actually.
I mean, I do think that, you know, coming back to the question, that certainly see the way that it's evolving. I see a number of different application areas, in particular around polar small molecules as well, that one can leverage as also a system. Mass spectrometry become faster and faster, more sensitive. Then once you couple that very small amount of sample that is required with the separation power of CE, is something that I definitely think that we're going to see potentially more key application areas that I think that can drive significant data generation that will be impactful. I think that we're getting close to the end. So maybe one more question here. The other hot topic that is coming through as well is in-source fragmentation. And this question is for Michael. It's all around metabolomics. So is there really a dark metabolome, or is it all in-source fragmentation? And that's a controversial question. I realize that.
Yeah, we have been discussing this, and this is getting a bit philosophical. I think the truth is somewhere in between, right? We have artifacts, and for the standards we have measured for our database, we have seen there are in-source fragments, there are weird adducts. So it's not only M plus H, M plus sodium, and that's it. There are dimers, trimers versus loss. It's all in there. So there are artifacts, measurement artifacts in there, but I don't believe that everything else is just in-source. So the truth is somewhere in between, and we have to make people aware. And I see, especially for novices, that they often believe, okay, there's one molecule, there's one signal, or said, no, there's the isotopes, there are the adducts, and there are the weird adducts in there. So please get aware here that this is very, very important. But still, there's a lot of things to be discovered. So I always tell my students, they say, you know, non-targeted, the idea is beautifully that you say, we would like to measure everything, right? But then you choose an extraction. So from everything, you go to this, right? Then you choose a specific mode that you say, I'm going with LC on this column, you go like this. Then I'm using ESI, and it's like this. So from this beautiful idea of measuring everything, at the end, you have only a snapshot. So I think left and right, there's still a lot of molecules to be detected, which are not in-source fragments.
Thank you, Michael. So that concludes our Q&A roundtable. So once again, I want to thank each and every one of you for attending the summit, for presenting, for being part of the panelists. Great insights, as always. And I'm going to pass it over to Tatiana.